Hi everyone! In this video we are going to talk about arc length in space, and that's going to be along a space curve. So basically arc length but in 3 dimensions, so 3D space. So the idea is that you have some curve in 3D space, and arc length is basically 1 unit of length if you were to travel along the curve. So we have what's called a base point. So I have this definition, or I'll give you a formal definition here, but some information. We can locate points along a smooth curve using this is going to be directed distance, and that's going to be from, or along the curve from a base point. So directed distance along the curve from a base point. And so the base point is going to be some starting point, which for this one here, that's right there at 0. So base point here. And so the numbers that I've written indicate which way is considered the positive direction of motion. So because I'd go from 0 to 1 and then 2, this is my direction. So my directed distance along the curve. So if this was a road, I'd be traveling along it, and these would each be some incremental distance on that curve. So let me give you the more formal definition here, and it's the formula for finding this arc length. And so we'll say our definition, the arc length, so that's what we'll be defining, and this is going to be of a smooth curve. And our curve looks like this vector function, r of t. So our curve is going to be defined by a position vector function that locates all the points along the curve. So r of t equal to x of t I plus y of t j plus z of t k. And this is going to be from some starting point, we'll say t equals a, to some ending point, which we'll say t equals b. And then just to be very specific here, I'm going to say traced exactly once. So we're not like circling around on our curve. So traced exactly once, and this is as t increases. Okay? And all of that is going to give us this arc length formula. So the length is equal to something, but basically, I should spell smooth right. You have a smooth curve in space. It's defined here by this vector function, and notice this has components for I, j, and k, and these are each going to give you some number or scalar. So in the I direction, j direction, and k direction, so that you can plot each of your points in space and locate your curve that way, or the curve that goes through those points. We're specifically saying from 2 numbers, so between like a and b, and you're only doing that path once. Okay, that's what we basically have there. So here's the formula. It is equal to, so the length is a definite integral from a to b of the square root of, this is going to be the derivative of x with respect to t squared plus the derivative of y with respect to t squared plus the derivative of z with respect to t squared, and this is all with respect to t, this integral. And so I want you to think about this really quick, because we can write this formula a little bit nicer based on something you know about. So if this represents our curve, or the position of something traveling along that curve, think about when you start taking the derivative like this. 2 things are kind of happening here. You're taking the derivative of each of these components of position. So that's the first thing. Derivative of position, that's velocity. Okay, so that's going to be our velocity vector function. That's the first thing. The second thing is, what does this format give us? This square root of these components squared and added, that should hopefully look familiar. That is magnitude, or length. So we can rewrite this formula as the definite integral from a to b of the magnitude of the velocity function of t with respect to t, or velocity vector function there. So here's our arc length formula. So next I'm going to give you the arc length but as a parameter. So let's get into that. Okay, so arc length as a parameter, we're basically thinking about the length on our arc as the inputs of our function, and we'll go through the difference in just a little bit. Each value of s, so s represents arc length, determines a point on the curve. So that could look something like this. So let's say you have your curve and you have some starting point, some base point. I think I called it P for point of some initial t value. And so if I know s, the length I want to travel on this curve, then that s value would determine the next point I'm going to plot. So let's say this is s, this distance, this length, and so that would now be my next point, P of t. So each arc length value determines the points on the curve. Then s, or arc length, increases, and it increases in the direction of increasing t. So as t gets bigger, so does s, arc length, and t increase in the same direction. So let's define this arc length parameter with a base point. So we have our arc length and the parameter, and so we're using the letter s for that, and this is going to be with base point P of t naught is s. So this time it's equal to s. S of t, so arc length is a function of t, and it's equal to our integral, which we're going to evaluate from our initial t value to just t in general. And basically the formula is the same for our length that we just wrote down. However, I am going to change the variable to capital T because I'm going to be plugging in t's, so I don't want to confuse it. So I'm just going to say this is square root of the derivative of capital T with respect, actually, let's go like this. Derivative of x, our I component of our position vector function, derivative of x with respect to capital T, quantity squared, plus the derivative of y with respect to capital T squared, plus derivative of z with respect to capital T squared, all of that in our radical, and then this is with respect to capital T. Again, just changing the letter because when I evaluate this, I'm plugging in lowercase t. And we can simplify this just like we did on the last version. This can be rewritten as the definite integral from t naught to t of the magnitude of the velocity of capital T dt. Okay, so let me identify the differences when considering t as the parameter and s, which we're talking about now. So we'll kind of look at two different ideas that we're talking about. Okay, so let's talk about this. Using t as the parameter and using s as the parameter. So I'm breaking this down so you can hopefully see and understand what's happening here. So if we want to locate a point on a curve, okay, if we have t as the parameter and s as the parameter, we do it two different ways. We locate a point on the curve when using t by using the position vector and then finding that point with plugging in t. So we basically plug in our t value into this position vector and we find that next point on the curve that we're looking for. If s is the parameter, if arc length is our input or parameter, we locate a point on the curve by determining its directed distance from the base point, P of t naught. So here's another way to think about that. Consider this idea. Here's directions to my house. Turn onto Main Street and drive for, over here I would say something like 20 minutes, and then you're there. 20 minutes, and then the house, something like the house is on the right. Okay, so for 20 minutes and house is on right. That part's not important. What's important is the 20 minutes. So the difference would be, here's directions to my house. Turn onto Main Street and drive for, let's say, 10 miles. And house is on the right. So the idea is the input, okay, what you're considering as how I'm going to travel on this road. I can travel on my road. As soon as I turn onto that road, I can say that my input is time. And I know when I input 20 minutes into time on this road, I will be at this house. Or if my input is directed distance, the moment I turn onto this road and I travel 10 miles in distance, I'm at the house. So these are the ideas here with the difference for t and s as our parameters. Now sometimes you kind of want to switch between these two, and so it's pretty simple. I'll just say it down here. So let's say to solve for t, and this is going to be as a function of s, so let's kind of get that in there, function of s, find s of t and solve for t. Okay, so I'll show you an example so you understand this one a little better. Here's this example. Find the arc length parameterization of this vector function, this curve. So r of t equals cosine ti plus sine of tj plus tk, and this is when our initial t value is 0. So we're asked for the arc length parameterization, so we're going to use our formula that we just worked with. Now remember what it needed. It needed the magnitude of the velocity vector function. So we have to start by finding that. So the derivative of our position function with respect to t is our velocity function. So let's differentiate that. And we get negative sine t I plus cosine t j plus 1k. Alright, now we need the magnitude of this because that's what we're going to integrate for our formula. So then the magnitude of our v of t is the square root of these components squared and added. So negative sine t squared plus cosine t squared plus 1 squared. And let's go ahead and simplify this before we integrate it. This is going to be sine squared t plus cosine squared t. So that might look familiar. That is your Pythagorean identity. So that's just 1. So this whole quantity is actually just square root 2. Okay. So then our arc length parameter s, it was the integral from t naught to t, just reminding you of the formula, of the magnitude of the velocity function here. And this is actually, I switched my letters in the formula, capital T, since we're plugging in little t. So we already found this value. It's actually just a constant. So this is going to be the integral from t naught, which we're told is 0. So let's just identify that we're plugging that in, until t, because it's going to be a function of t. And then our integrand is square root 2 dt, capital T. Okay, so now if we integrate this, this is going to be square root 2, capital T, evaluated from 0 to little t. So there's the reason why I was using a different t, just because now I'm about to plug in little t. So this is square root 2, little t, minus 0. So that's going to be what we keep right there. Okay, so what does this say? So we say s of t is square root 2 t. And just to make it a little bit more concise, I'm just going to say s, because I think that might help a little bit with you seeing what I'm trying to say here. So I'm going to rewrite my function because I'm actually asked to find the arc length parameterization of this r of t function. So I'm not quite done, but I do want to mention something here. This is basically telling you the relationship between arc length and t. So one way to think about this is maybe my example like driving down a road. So I want you to think about something. To relate time and distance, if you considered driving at 60 miles an hour, just think about this for a moment. If you drive at 60 miles an hour, you'd be going 1 mile per minute, right? Because 60 minutes in an hour. So that would be a one-to-one relationship between time and distance, or arc length. 1 mile in 1 minute. 1 mile distance, 1 minute of time. That would be 1-to-1. This is not quite 1-for-1, a ratio, because this is saying for every 1 arc length unit, I have square root 2 of time units, or every 1 arc length unit is 1.4 time units. So just hopefully you can kind of grasp what I'm saying there about what this is representing. So now we need to basically rewrite this function up here in terms of s, arc length. So all you got to do, and we mentioned it just a minute ago, is solve for t, and then we can plug it back in here. So if we solve this for t, just divide by square root 2. So we have s divided by square root 2 equals t. And you can rationalize that denominator if you want. I'm going to go ahead and just leave it like that. And so my arc length parameterization for this curve, I'm just going to rewrite it right below, is the following. So now it's officially r of t of s, because t is now a function of s based on how we rewrote it there. So this is going to be cosine, instead of t is the same thing as s over square root 2. So cosine of s over square root 2, and that's I. And then plus sine of t, which is now s over square root 2, j, and then t is s over root 2, k. And that would be the answer. Okay, so we parameterized that curve using arc length. So now if I input numbers for s, each number represents a unit of arc length, whereas t might represent something like 1 unit of time. So I'm going to give you a little bit more, and then we'll finish off with 2 examples. Alright, so 2 more pieces of information for you here. Speed on a smooth curve, and then the unit tangent vector. So we've talked about speed before, and it is the magnitude of the velocity. But now that we learned about arc length, if you can parameterize your curve and consider arc length, this speed is actually equal to the derivative of the arc length with respect to t. So we had that equation we just had down here, s equals square root 2t. So if you were to, so I'll just rewrite it really quick. If you were to differentiate this with respect to t, that would actually be the speed. Okay, and then your unit tangent vector. So you know both of these words here, just put them together. Unit means length 1, unit vector, and tangent means the vector that is tangent to your curve at that point. But also remember how you get that, it is from the derivative of position. Okay, so we denote that with capital T. That's our unit tangent vector. So when you see that, it's usually unit tangent vector. And so remember, if you're finding a unit vector, you're taking a vector and you're actually dividing by its own magnitude. And if it's tangent, that's the derivative. So if you're thinking about your curve, the derivative of the curve or the position is the velocity. So it's the velocity over its magnitude. But now in terms of arc length, if your curve is parameterized with arc length, you can actually just differentiate your vector curve function, r, with respect to s. And that's going to actually give you that unit tangent vector. So let me add a little bit here. So I'm just going to say where v is the derivative of r with respect to t. And it's the vector tangent to the curve, r of t. And then a quick note, and then we'll get into the examples. If the magnitude of the magnitude of v, so the speed here, magnitude of v is 1, if you get this when you're working, then t is actually the same as s. It's that situation we talked about where 1 unit of time lined up with 1 unit of distance. Okay, so then t equals s, and then what that actually implies, actually we'll say it like that, is that your position function, r of t, is already parametrized by arc length. So is parametrized by arc length. Okay, even if it looks like it says t, if you find out that this is 1, then t and arc length are lining up, they're the same value. Okay, so let's take a look at this example. So find the unit tangent vector of the following curve, right? It's just a few quick steps with derivatives on this one. So tangent, think derivative, and then unit vector, we have to divide by the magnitude. So we're going to start by finding the derivative of our position curve function, vector function here, which is v. So derivative of r is v. And so just differentiate the components. So this is going to be -3 sine of t I. Over here, this is going to be 3 cosine of t j. And in the back, that's going to be 2t k. All right. Now, I need the magnitude of this because for my unit tangent vector, I have to divide by the magnitude. So the magnitude of v, we're going to take the square root of -3 sine t squared plus 3 cosine t squared plus 2t squared. Okay? And let's simplify this a little bit. This is going to be 9 sine squared t plus 9 cosine squared t plus 4t squared, all inside the square root. And then if you factor out a 9 here, you're going to be left with sine squared plus cosine squared of t. So that is your Pythagorean identity again, which is 1. So this equals square root of 9 plus 4t squared. Okay, so then to answer this question, the unit tangent vector, I found the derivative of the position vector, this curve, and I have to just take that derivative and divide it by its magnitude. So we have that t, which is what we were asked to find, the unit tangent vector, equals v over its magnitude. So that is, go right here and take v and divide it by that magnitude. So -3 sine of t divided by square root 9 plus 4t squared, and that is the I component. And then we just do the same thing for the j and k components. So 3 cosine t divided by this magnitude, and then that's j, last 2t on top over this magnitude, and that's for k. All right, so there's our answer to this one here. We're going to do one last example, and it's going to involve this same curve. All right, so let's take a look at this last one. So find the arc length parameter along this same curve, and this is if t naught is 0. All right, so we already did some of the work, but this is actually a fairly complicated one. That's partially why I want to show you. There's a lot to kind of remind you of in this example. You'll see it as we do it. So we need the arc length parameter, that formula required using the magnitude of the velocity, which we already found. So s of t is what we're asked about, and we know that it's the definite integral from t naught, which is 0, until t, and it's going to be the magnitude of the velocity vector function, which we figured out was square root 9 plus 4t squared dt. Okay, I'm using capital T's just because I'm eventually going to plug in little t. Alright, so how do we integrate this? Alright, first thing to remind you, integrate something like this, trig substitution. So let's talk about that for just a minute. So your trig substitution is going to be required here in order to integrate this function. Now, if you remember how that goes, that's good. If you don't, let me kind of remind you real quick. So I'll just draw a right triangle over here and then think about what I'm given. So I have this integrand where I have something squared technically plus something squared inside the square root. So that's the sum of the squares of actually two legs of your triangle. So that quantity you can say is your hypotenuse here. So that's square root of 9 plus 4t squared. And then you just say, well then this is one leg squared and that's the other leg squared. So you can say that that leg's 3 and this leg is 2t. Because when you square and add them, you get this inside the square root. Now, if I'm going to substitute for t, because that's how my trig substitution is going to go, I'm going to plug in for t here. In this case, I'm actually going to use tangent. So I'm going to say tangent of theta is opposite side over adjacent side, so 2t over 3. But I need to plug in for t, so if I solve this for capital T, that's just going to be 3/2 tangent theta. Okay, that's what I'm going to plug in. I also need to change dt as well. We'll do that in just a second. So we have the integral. I'm changing my variable, so I'm going to kind of distinguish here that this is still limits of integration in terms of t. So from t equals 0 to t equals little t of square root of 9 plus 4 times 3/2 tangent theta quantity squared. And then that's in the square root. And then dt, now let's find that. The derivative of t with respect to theta from our choice for t right here is just going to be 3/2 derivative of tangent theta, which is secant squared theta. And then if I times this d theta over here, I can go ahead and say that that's dt is equal to 3/2 secant squared theta d theta. So that's going to go right here. So that's 3/2 secant squared theta d theta. Okay, so first part done. We used trig substitution. Hopefully that kind of looks familiar or kind of reminded you of some things that you learned in the past. And so let's start simplifying. Right here, the whole point of using this substitution is so that it becomes more possible to integrate it. And so let's see what happens with this square root part. This is going to be 9 over 4 tangent squared when I square this. So the 4 on top and bottom are going to divide out. So we just have 9 plus 9 tangent squared theta inside of our square root, which then if we factor out the 9, that's going to be 9 times 1 plus tangent squared theta. And again, you kind of ask yourself, why did I even use this substitution in the first place? Because now, here's why. You can actually rewrite this. So the next reminder is trig identities. So this is a trig identity if you say that this is secant squared theta. So this is like a version of your Pythagorean identity right here. So you're subbing that in. And so that becomes, let's kind of just keep going this way with it, square root of 9, which is 3, square root of secant squared theta, which is secant theta. So that's this whole front part of my integrand times this 3/2 secant squared theta. So let me put that together. And we have, if I say this whole square root became 3 secant theta times the 3/2, that actually becomes 9/2, and I'm going to put that in the front. So this 3 times this 3/2. And then I have a secant squared theta times 1 secant theta, so it's secant cubed theta, d theta. Okay, so now you ask yourself, how do I continue? I'm trying to integrate this. I started here, I had to use trig substitution and actually a trig identity. Now I'm here. How do I integrate secant cubed theta? This one requires integration by parts. So let's remind you how that one goes. So integration by parts, let's just talk about that real quick. The formula for that, the way that I write it is the following. the integral of u dv equals, so that's your original integral, that's what we're working with here, it equals u times v minus the integral of v du. So you rewrite one integral that's complicated to work on in terms of this other integral that's hopefully easier to figure out. So what you have to do in this case is you actually have to choose u, and then you find du, because you need it here, and then you choose dv, let me give myself more room. You choose dv, because you need it, it's from here, and then you find v, because you need it there. So from here, this is really kind of one product here, but if we break it apart, I can kind of identify what I'm going to call u and what I'm going to call dv. So I'm going to separate this and say that this is 9/2. And real quick, technically I still have limits of integration. I'm just going to sort of leave them off for a little while. At the same time as well, I'm going to go ahead and leave off this 9/2. So just some notes for myself to go back to later. My limits of integration, I've got to come back to those. And also, just to save us some writing and keeping track, I'm going to leave off this 9/2. So I'm going to say that integral of secant cubed d theta can be broken apart as the integral of secant theta times secant squared theta. And then that way part of this is u and the other part's dv. So I'm going to say u is secant theta, and then that means everything that's left is the dv. So dv is secant squared theta d theta. And then I find du by differentiating secant theta. So that's just going to be secant theta tangent theta. And then technically there's a d theta back here. Okay, that's just from remembering the derivative of secant. And then if I find the antiderivative of secant squared, because I need, this is the derivative already, I need to go backwards. So what function has the derivative of secant squared? Well, that's tangent. So tangent theta. Okay, so then let's plug into our formula. So this equals u times v, which u was secant theta times v, which we just figured out was tangent theta. And then minus, because the formula has minus, the integral of v, which we figured out was tangent theta, times our du. So then du was this part, secant tangent. So secant theta, tangent theta, squeeze in the d theta right there. Okay, so the idea is that this should be getting more manageable. I know it doesn't quite look like it, but it really is. We'll keep going and we'll get there. But so far we had to use trig substitution and integration by parts. So I need to clean this up a little just so we can stay on track. Let's go ahead and move it up here. I am going to end up needing that triangle again, so I'm going to try to leave that visible. We can sort of take off all this other stuff though. Okay, so my reminder's over here in the corner, and we kind of just need to keep this part here. Okay, so what we have going on so far is, remember I'm leaving off the 9/2 for just right now. I have on the left side of my equal sign the integral of secant cubed theta d theta. That was this part. We did break it apart to say what u and v dv are, but I'm going to go and say that's my left side. The right side is this here, all of this right here. So it equals u times v, which was secant theta tangent theta, minus the integral of v du. So let's put this together. This is the tangent times the secant times the tangent. So that's really tangent squared theta times secant theta d theta. Okay. From here, does it look more manageable? Not in this form, but it actually is. So you can try u substitution here because you're still having to figure out this integral. We did sort of break this down, this integral, into this one, in terms of this one. U substitution won't work though. So what you really actually want to do here is go back to your trig identities again. So your trig identities, tangent squared theta is actually secant squared theta minus 1. So we can rewrite that. And so what we can do here is distribute. We can say that the secant theta here, so this is secant cubed theta minus secant theta if we distribute this secant theta into this quantity. And so that's what we'll be integrating. And I know you might, if you see that, you say, wait, we were already working with integral secant theta and we had to do secant cubed theta. Now we're seeing it again. It's okay now because we can actually just move this one over. So let me break this into 2 because this is technically minus this whole quantity here. So if I break this apart, this is minus the integral of secant cubed theta d theta, and then the minus and the minus here becomes plus the integral of secant theta d theta. These are the 2 integrals we're left with to figure out. This complicated one, we actually get to just move it over, and this one, we know this one. Either you know it because you've memorized it, or you can derive it, or you have a table available to know this one. So what I'm doing technically is, if I sort of bring this down so you can keep track, this is secant theta tangent theta equals integral of secant cubed theta d theta. I'm moving this term over because it is an equation, so I can go ahead and say plus secant cubed, integral of secant cubed theta on both sides. Okay, so we're moving this one over, and then on the left side we now have that this is 2 times the integral of secant cubed theta, and that equals secant times tangent, secant theta times tangent theta, and then all that's left here is this plus the integral of secant theta. Okay, so that integral, when you integrate secant theta, you get natural log of the absolute value, secant theta plus tangent theta. Okay, and so now we just sort of have to bring stuff back in. I had left off my limits and I left off the 9/2. So we were trying to find this integral, 9/2 of integral of secant cubed theta d theta. So I have to actually divide out this 2 to get that integral we were looking for, and then bring back in this 9/2. Okay, so let's move this stuff. Let's divide out the 2 really quick. So I have integral of secant cubed d theta. I'm dividing by 2. So that's 1/2 secant theta tangent theta plus 1/2 natural log secant theta plus tangent theta. Okay, now let's bring on that 9/2. So 9/2 of this. So we times everything here by 9/2. So I'm just going to go ahead and multiply it out here and say 9/2 times 1/2. That really becomes 9/4 in the front here. Same thing over here. So this is 9/4. Okay, so that was that one reminder for myself. The other one was I still need to figure out what this equals if I plug in my limits. So the integration part, we figured that out. That was pretty tricky, but we did everything. We used a lot of tricks and tools that we learned in the past. Trig substitution, trig identities, integration by parts. Okay, so a lot of things we've learned in the past. From here, we have to, if you notice, technically plug in for theta, but I have my triangle there to figure out what secant of theta is and what tangent of theta is. So you can solve for theta. It would require that you use inverse tangent, but I'm just going to leave it in terms of my values from my triangle and not have to actually use the inverse function. So here's what I'm saying. Everywhere in my expression here for my answer, I only have to figure out tangent theta and secant theta. So back from this triangle, let's sort of just focus on that for a second. So from there, using the definitions of our trig functions, tangent of this angle theta is opposite side over adjacent side. So everywhere I see a tangent theta, I can go ahead and say 2t over 3. So here and here. I also need secant of theta, and secant is a reciprocal of cosine, and so that's going to be the hypotenuse over the adjacent side. So it's going to be square root of 9 plus 4t squared over 3. So everywhere I see a secant theta, I'm going to go ahead and plug in that expression. So this equals 9/4 times, okay, I'm starting to plug in now. So I'm plugging in for secant theta, which is this. So that's going to equal, or times, square root 9 plus 4t squared over 3. Times tangent of theta, which tangent of theta was here. So we're going to plug that in here and here. So that's going to be 2t over 3. So that's this quantity right here. And then plus 9/4 natural log, absolute value, secant theta was square root 9 plus 4t squared over 3 plus tangent of theta, which was 2 plus 2t over 3. All right, we're almost there. Last part, we still actually need to plug in what t was, our limits for t. So this whole thing, this is actually s of t, but we were given that t starts at 0, and then we want this as a function of t, so then we go from 0 to little t. So we're going to evaluate this from t equals 0 until t equals little t. So let's fill that in. Okay, so got that part there. So let's get rid of some of this. Okay, and so from here, I'm plugging in a little t everywhere I have a capital T. And then let's just talk about what happens when I plug in 0 really quick. The lower limit, plug in 0. This term is still going to be a 1, but this term is 0. So that means that whole term goes to 0. Back here, this is going to be 1 plus 0. And if you recall, natural log of 1, e to what power is 1? The answer is 0. So natural log of 1 is 0. So when I plug in 0, I get 0. So what we basically just have to end up writing here is s of t is, let's see if we can put anything together. We kind of can. Let's make our lives slightly better at the end here. We're going to say 9 divided by 3 divided by 3. So that all divides out. And then 2 divided by 4, so that turns into a half. So 1/2 square root of 9 plus 4 little t squared times, that's now little t as well. So let me just make sure I have it clear, but that's little t right there. All right, that's from simplifying this and plugging in little t. And then plus, so plus 9/4 natural log of, and we can put this together because it's the same denominator, so we can say square root of 9 plus 4 little t squared plus 2 little t all over 3. Okay, we did it. It was a long one, but I'm hoping that by going through this you were reminded of a lot of your integration techniques. Okay, so this is now the parameter for arc length for that curve function that we started with. So if you plug in t, this is the relationship basically between t and s. Like thinking of plugging in time versus plugging in distance. This is the relationship. All right, take care.